Alright, so now just picking up where I left off in the previous video, and just as a reminder, the link to the playlist and the previous video are in the description of this video. So we got up to this point where this is the least squares, weighted least squares procedure. We want to minimize this. And then once we arrive at the equation for the minimization of that, hoping that it will bring us to something that looks like the ending of our proof for the maximum likelihood equations. Because remember, the paper said that the solution of the maximum likelihoods is equivalent to this weighted least squares procedure. So let's go ahead and continue working on this weighted least squares and see what we get. So when we want to minimize, basically what we want to do is we want to take the derivative with respect to beta, and then we want to set it equal to 0. Okay, so we'll take the first derivative, set it equal to 0, and then that will be that'll be our solution for what beta hat should be, or what our least squares estimator is. Okay, so I have y, x, beta. I'll go ahead and take the derivative. Just for consistency, I'll go ahead and keep the hat on top of beta to show that that's our estimator, not the true value. Okay, and then, okay. So first thing I want to do is actually go ahead and simplify what I have here, and then I'll take the derivative after a few steps here. So I'll go ahead and distribute this w, and actually I'll bring in that transpose. So this will become y transpose. Transpose of x times beta would be beta transpose x transpose. And then I'm going to bring the y in, so I still have parentheses around here. Bring the w in, bring the w, so w times y minus wx beta hat. Okay, so I haven't taken the derivative yet, still need to do that later. All I'm doing is simplifying what I have here. Now I can go ahead and FOIL, so I'll have first, let's see, minus y prime times w x beta, okay, minus w or beta prime or beta transpose x transpose y wy, and then the last one would be plus beta transpose x transpose wx beta transpose. Okay, and I still need to do the derivative later. All right, right here, notice that this and this are the same. Okay, and you might be saying, what? They don't look like they're the same. So let's go ahead and first let's do our dimensions here. So y transpose, it would be 1 times n. W is an n by n matrix. X is an n by m matrix, and beta is an m by 1. So basically this is a scalar, right? Because you see everything cancels and you're left with a 1 by 1. So it's a scalar. So its transpose is equal to itself, right? The transpose of a scalar is itself. So I can basically find the transpose of this, which would be beta transpose, x transpose, w transpose, y. Okay, so you're seeing, oh, okay, they're similar, but there's a transpose there and there's no transpose there. So what's going on? Well, remember, w is a matrix with the diagonals are not 0, but then all of the diagonals are 0. So W transpose would just be itself, right? If you were to transpose this matrix with the off diagonals being 0, you would get itself. So that basically, these guys are the same because W transpose is itself, so they're the same thing. So this equals, I still need to do this integral to okay, leave that there. Let's see. I think actually, let me write this the other way. So you can write it either one because they're identical, but I'm going to write it like this. Okay. Okay, so now I'm ready to go and take the derivative. So this first piece doesn't involve doesn't involve beta. Doesn't involve beta. So because it doesn't involve doesn't involve beta, it will become 0. The second piece has a beta. When I take its derivative, basically that beta will drop. Okay, and then this last piece has 2 betas, which is kind of like beta squared, and so its derivative would then be 2 times x transpose wx beta. Okay, so it's when you take its derivative, it's basically like bringing down the square. Okay. All right. So now I'm going to go ahead and rewrite this. I'll bring this piece over to the other side. Okay, and then lastly, you see the 2's will cancel. So I'm left with x transpose x beta hat equals x transpose, just like that. All right. So is that the same thing that we had up here? The answer is yes, but we need to show that. So first, let's write A using matrix notation. So you see it's written here. This A, you can write this. This is the same thing as writing x transpose wx. Okay, they're identical. You can show this. And then let's see, what about R? R is the same thing as x transpose w y. Okay, you can see that there. Using matrix notation, that's basically the way you would write it. Okay, so let's see. Now I have everything written on 2 different sides, but basically this is what A is. So I have A times my newly estimated beta, and this is what R is. So we've shown that using this weighted least squares, right, procedure, you get exactly the same thing as A times beta, whatever your current estimated beta is, equals R. Right? Because beta, when you have beta plus the change in beta, this is your change in beta, this is your prior estimate of beta. So your prior plus whatever change happens will be your new estimate, which is what beta star is. And that's exactly how you're going to figure out what beta hat is. That's your current estimate of beta. Okay? So you also might be thinking to yourself, well, I haven't mentioned any iterations here. So what's going on? Well, basically, if I go back to my paper, right, mu, y, and v, these are all whatever your current estimates are. And so what you have to do is you have to go through and what you'll do here is you'll solve for beta. So you'll have beta hat equals A inverse times R. You'll solve for beta, or in the more, like if you were to write this not using A and R, but basically beta hat equals, you could take the inverse of both sides, X transpose like this, inverse. Okay, so you start with whatever some current estimates are. So you start with some current estimates of mu, y, and v. And then you solve for w and y. And then you use this equation and you get a current estimate of beta. And then you use that current estimate of beta again to figure out an updated mu, y, and v, and then you continue like that. So that's the iterations that go on. All right, and I think that we'll be talking more about that those iterations here in the subsequent sections.